I made a lot of slides. I try to overwhelm with a show of force. So I might have to go quickly through them. Just let them wash over you, and if you have questions about anything in particular, we can go back to it at the end. So the big thing that I did for Filecoin was I led the proofs that led the team that made the Filecoin proofs. And there's a page about it here if you want to see how cool they were. But the main thing is that we took some somewhat dated technology and really pushed it to the limit. So we had very large circuits, and we did a very high volume of those proofs every day, and we do them really quickly. And Supranational did a lot of the work helping optimize that, and you'll hear from Kelly later. So in the process of doing that, we also really experienced the pain of trying to do things with SNARKs. Writing them is really hard, and getting them correct or to a state you believe is correct is really hard. So the whole development cycle is like, I don't know, things that should take like an hour can take like months to get all the way through the pipeline. And at the end of the day, what you can do is still quite limited. So this talk is going to be sort of about the past, present, and future of Lurk. So this is the starting point for that. When Filecoin launched, I started asking, what could we do with a little bit better technology and a little more time to work on it to solve some of these problems or attempt to make inroads. So we're going to look at SNARKs and their limitations. We're going to look at how that problem fits solutions we know about, details, implications, etc. Okay, so what are some of the limitations of, when I say SNARKs in this part of the talk, which is a talk that I gave about a year ago first, when this project was much earlier. Here, I mean SNARKs as we had come to think of them then, sort of the last generation, like Groth 16, if that means anything to you, SNARKs like what we use in Filecoin currently. Okay, so people have probably seen this before. If you don't know what SNARKs are, they're zero knowledge, succinct, non-interactive arguments of knowledge. And you'll have to look that up, but we'll go over some pieces of it. And we can make small, fast-to-verify proofs of arbitrary statements. And the general form of a statement is, I know of some values such that some arithmetic relationship holds between them. That's what a SNARK gives us, more or less. And so when we say a circuit, we mean something that looks kind of like this. It's what you think of as a circuit, except instead of Boolean logic, we have arithmetic. And it's arithmetic over a finite field. So down at the bottom, you see this thing with these named variables, and then a witness, which is essentially an assignment of those variables that we claim has the relationship that the circuit specifies. So what can you do with these things? In bounded circuits, we say bounded circuits because we have to do a trusted setup, and there's a maximum number of constraints of these arithmetic relationships we can specify in a single circuit. So Filecoin was really big. We had over 100 million constraints possible. So that sort of sets the limit of what we can do. So we can prove any NP statement, but only up to a certain complexity limited by the size of the circuit. This non-determinism is important because it lets us do things like prove preimages of hashes. And we don't have to do that by taking a hash digest and then computing the digest from the hash somehow. We think that's not possible to do. But if the prover knows the preimage as a secret, then he can prove that the preimage hashes to the digest without actually revealing that. So that's the zero knowledge part. Let's look at the limitations. So in general, we can use SNARKs to prove the results of verified computations. But if the computations to verify are arbitrary Turing-Complete programs, there's going to be a problem because in general, we don't even know if Turing-Complete programs terminate at all. So they could have any arbitrary amount of work in them. But I've already told you that there's only 100 million constraints that we can get into a big circuit. So in the presence of unbounded loops and conditionals, this requires the circuits to be arbitrarily large, and we can't do that. So that's basically the problem. So an example, loops Loops can be unrolled in circuits, so instead of saying, do this 10 times, you just do it 10 times, incrementing some counter like you would write in your code, A equals 1, A equals 2, A equals 3, etc. But the problem is you're going to have to actually unroll that and pay the cost of whatever the largest number of iterations that you might have is. So it's inefficient in the best case if you have a lot of variation, and in the worst case, you just can't do it. So in practice, you just can't do it. If you need arbitrarily large loops. And similarly, conditional control flow doesn't really work the way you think it would if you're a programmer. You're used to thinking, okay, you have an if, and depending on if it's true or false, we will execute either the true branch or the false branch. But actually, in a snark, you have to calculate both because you don't know which it's going to be. So all the calculation has to be laid out in that circuit. Here's an example that just makes it really obvious. If we have a loop that has an if, that has expensive things and expensive things within it, this is just going to blow up, and it's going to be intractable. So we would like to figure out how can we use a single circuit to implement a Turing-Complete language, like a true Turing-Complete language. So what do we mean by that? Read your computer science books, something about a moving head and reading and writing on an infinite tape. Who cares? Nobody uses actual Turing machines, but everybody kind of intuitively knows what they mean. There's a very special case of the universal Turing machine, which is basically a machine that can take as input a description of another machine and execute programs for that machine. And this is basically like a programming language interpreter or a runtime for a programming language. So this was really cool when it was first thought of, and now it's just we take it for granted that these kinds of things can happen. SNARK circuit encodes just one single fixed size calculation, like a Groth 16 circuit that you've done a trusted setup for. The changes are really error prone, take a lot of care, and you probably need to have them audited, et cetera, every time you change that circuit if you're using it in production. And it's just very low level. It's sort of like writing an assembly language, or maybe like writing in Verilog or something like that. It's not at all like normal programming, even if you have libraries that are supposed to make it more convenient. So what we'd like to do is, just so we have a universal Turing machine, we'd like to have a universal circuit, that we write the circuit one time and then we feed to that circuit recipes or instructions for turning itself into some other machine so it can run other programs. So the input is going to specify an arbitrary computation rather than just being a single input to some predetermined calculation. It is a predetermined calculation, but it's a very special predetermined calculation that implements the universal circuit. So the input is going to be some computation, and then the output will be a result. And it can be any computation in and any result out. And then, because this is a snark, we get a proof of that, and it'll be fast to verify. And we can do it. Yay. This was exciting a year ago. Now we've been doing it for a while. So the trick is recursive snarks. This is just a diagram showing you what proof-carrying data looks like, which is essentially that you can have these individual compute nodes that perform some computation, and those computations get fed to each other. With general PCD, the shape of those compute graphs can be an arbitrary DAG, and there's a special case called IVC where it's just a linear graph, and that's actually all we need for something like Lurk. So I don't know why this title is there. It's silly. But anyway, the point is we can take that problem and find a solution that fits it. So we want to make Turing-Complete programs. We're going to implement a universal circuit. Here are the tools we have. Merkle RAM machines from snark-friendly hashes. So a RAM machine is basically a Merkle tree of data that you have a commitment to, and you can feed into your circuit, and then this represents the claimed state of some virtual machine, and then you can alter that in the proof and then emit a new one showing that you have a new state. So we're going to use that. We're going to use recursion. We're going to use finite field arithmetic. And then we'll just use the ordinary circuit constraints that we've been using all along. And this is actually all we need to do to implement a universal circuit the way that Lurk does it. So the fun thing that we thought of was, okay, lambda calculus is more interesting than Turing machines. It's Turing-Complete. Everybody knows this. And the original Lisp from McCarthy's 1960 paper, Recursive Functions of Symbolic Expressions and Their Computation by Machine, basically describes a very small set of operations that you can use to get something that's computationally equivalent to the lambda calculus. And it turns out that the things that we just described above are enough to implement a simple Lisp and a SNARK. So maybe we'll do it that way, just because it seems like it'll work. So Lisp and a SNARK, we'll call it Lurk. So what is Lurk? Lurk is a Lisp. When we say program execution, we mean expression evaluation. So any data or any datum that's expression in Lurk can be evaluated. So there's basically, our one function we get is a function called eval that takes an input and gives you an output. I'll show lots of examples of this later, probably really fast too, because I have a lot of slides. So Lurk is a data language. This is important. This means essentially the inputs and outputs of Lurk programs are content addressable. You can create them from a description of the data, like a textual description, by hashing that data, just like an IPLD data structure, if you know what that is. And that turns out to be really important for uses as well as for the implementation. So I kind of said that. What's nice about this is that there's no separate compilation step at all. You just take your data, turn it into hash, or maybe you already have the hash of it because it's content addressable data. You grabbed it off the internet, maybe it was in Filecoin, or maybe you did write your program and you just have this very dirt simple parsing process that content addresses your data. And that then can be fed into the prover. There's not an extra step. So code is data and data is code. This is kind of a Lurk mantra. And that's it. Because of the properties of Lisp, if we can figure out how to make this implementation, we're going to get something that is Turing-Complete with unbounded recursion in the way that we had hoped for. And that's pretty much the goal. And because of the structure of this, we can compose these things just the way you would think if you're used to using expression-based functional languages. And you can do this over private data because of the zero-knowledge property of SNARKs. So how does it work? Basically, Lisp has a fundamental memory allocator called cons, which lets you take two things, glue them together, and gives you a pointer back to it. This is your heap allocation. We are going to do this in a virtual machine, in a RAM machine, so our cons is a binary hash. We take two expressions, hash them together. That hash is effectively a pointer to them. And if I can prove that those two expressions hash to that same pointer, I've essentially dereferenced it, and I can do that in a SNARK, and it'll have all the properties that you hope that it would have. There's a little more detail that I'm hiding here about type tags. I might mention it later, or you might have to imagine it. So I said this before, but eval is our universal function that implements our Lurk interpreter, and we're going to implement that in a circuit. It's a little more complicated. I think I'm going to mention that. Yeah. So what actually happens is, as well as an input expression, we carry around a lexical environment, which is part of the execution process, and also a continuation. And so we use continuation passing style. And this lets us slice a single evaluation, which remember could be extremely long computation, into uniform steps, each one of a tractable size. So that means that we have an explicit continuation, which is one of the arguments to that very small inner circuit that we're going to use. And then these optional extras are RAM and ROM. These are things that are coming in the future of Lurk that will make things more ergonomic. So this is just a somewhat silly attempt to visually show how it works. So this blue dot is supposed to be the expression, the green rectangle is the environment, and the red arrow is a continuation. So for example, if I have the number 123, we're pretending that that's the digest that corresponds to this green circle, and we're going to look it up in the environment. We find the value 9. Actually, I don't really understand what this slide was supposed to be. It was a long time ago, but the important point is that we can look up each value of, so we have, in the next line where there's this circle and square, this is a function call, so we look up the circle, find that it's an f, we look up the square, find that it's an x, and so the whole expression represents a function call, f of x, and then we'll continue to evaluate that. This is a really bad explanation of continuation passing style as we use it. So now here's an example of this actually working. This is from a year ago, so if you know Lurk now, there might be slight differences. But in just a few lines of code, we're defining a double function, a square function, a for function that's going to let us loop in the way that we hoped we'd be able to, arbitrarily large loops. And then I have a function called just one that only executes one branch of its conditional, and then I have one called both that is going to look at both branches of the conditional. And let's look and see what happens. So you can see this 4, 3, 9 square. We get all the squares of the numbers between 3 and 9. And then this 325 iterations is important. This is something that Lurk always gives you because every time it evaluates an expression, it breaks it down into these individual reduction steps, and this is telling you how many of those there were. So you kind of get a performance monitor built in. So that's 325 iterations. This just one, if I pass it nil, it doesn't do the thing, so it takes 8 iterations to run that function. If I pass it t, which is true, it does this loop, and you get one branch, and it takes 4,748 iterations. And then if we say both, you can see that it's performing both branches, and it's a lot more expensive. This example might not be the best example, but it's the one that I used a year ago, and it's generally showing that you're getting a different amount of work depending on which branch of the computation you take. Okay, so what are the implications of this? There were things that we thought were impossible. Now they're possible for us. You want loops? We have loops. Conditional control flow, we have that. And we have unbounded recursion. Yay, we did it. Okay, so now we can actually write proofs that feel just like writing programs. It's actually really easy to write this. If you're familiar with Lisp, then it's super, super easy. If you're not, then you need to take like half an hour and learn how to write Lisp, and then it's pretty easy. So all these examples, I just wrote these things down and did it, and I promise it would not have been easy for me to write those in our previous tech. So this was really exciting, again, a year ago when it first started to be possible. What's interesting here? So this non-existent proofs thing is kind of interesting, which is basically, if I have a data structure that contains, let's say it's just a list and it has n elements in it, I can actually easily give you a proof that something is not a member of that list, which is not easy to do in a normal snark. There are ways, but you have to use very special data structures. But the point I'm making here is if you can write a program to do it, you can do it. And I can just write a program to check for the existence of a value in a list, and boom, I can have non-existent proofs by proving that the result of evaluating, is X a member of this list, evaluates to nil or false. It doesn't. So a lot of this work came out of thinking about Filecoin proofs. We did a lot of stuff with Merkle trees and Merkle inclusion proofs, and again, at the beginning of this process, it was really exciting to see that all these things that we thought of as explicit Merkle proofs just sort of disappeared. Now a Merkle inclusion proof, where we want to check whether a value occurs in a tree, it's really as simple as just looking and accessing the data. And if we can see it, it exists. If we can't, it doesn't. And similarly, if we want to update a Merkle tree in a provable way, like updating the state tree of a blockchain or something, we can really write it just exactly like we would write ordinary code, and everything works and is provable the way you think it should be. All right, and these are examples of that. Okay. So now with this model, whatever else you get, you really are just writing programs and you get the proofs for free. This is what I was going for in the first place, and that gives it to you, which is exciting. So from there, we went on to make the language more expressive. I'm pushing these things and saying different things. The main point is that we can use all the tools of programming to write proofs. All right. So now I'm just going to give you a bunch of examples. This, the first time I gave this presentation, I only had 7 minutes for it, so I'll go fast just so you can see the idea. There's a blog post that goes through this in a lot more detail. I actually recommend it if you're interested in understanding. You will understand how the Lurk language actually works, what you can do with it after you read that. But as you can see, I add 2 to 3, I get 5, it takes 3 iterations. Cool. Cons, okay, this 1.2, that's a literal pair. I can make all kinds of trees using cons. So I can basically build any Merkle data structure I want to out of conses. I get conditionals, but only one branch is actually evaluated. So you can see, depending on whether this is true or false, we get 6 or 8 iterations. This is sort of a redux of the thing I showed on the previous slide. Quickly, we can bind variables. So we assign 9 to the variable A, and then we can use it. And we add 1 to it, and we get 10. We can create anonymous functions. This is where it gets kind of cool. Lurk gives us all the functional programming stuff that you might want to use. And we'll show some examples of that towards the end. You can immediately apply an anonymous function. So for example, here we write a square function, apply it to 5, we get 25. A lot of this is boring. Okay, here's sort of functional programming examples, like I can return a closure from a function. Study that on your own. We have a special construct that we need to use if we want to use recursive functions that call themselves, but we can do it. So here's an example of a function to take the length of a list. And you can see it's very simple. And we can implement loops. Here's just another loop example. I kind of like my for example from before, but here's, if we want to write something that sums all the numbers up to some number, it's just a couple lines of code. That's pretty easy to understand. And not only can functions return functions, but we can take functions as arguments. So here we're defining a map function and then passing square to it and squaring the elements of a list. And again, this is all, you get this primitively out of our very small Lurk circuit. So let's just breeze through some of these. The main point to take away from this is that Lurk supports higher order functions natively as content addressable data. So we can do cool things with that. Okay, commitments. The idea here is that we want to use cryptographic commitments. We want to say, here's some hash, and it represents some data, but you don't learn anything about that data from the hash, but I can give you a proof later that I'm using that same data, even if I still don't tell you what the data was. So we have explicit support for that in Lurk. So for example, if I commit the number 123, I get this very long, about 256-bit value back. So then I can open that commitment, and because I, the prover, actually know the pre-image, I'm able to compute this, and I could give you a proof. If I didn't know what the pre-image for this commitment was, I would just not be able to produce this proof. Okay, so functional commitments. This is where it gets cool. Because functions are first-class data in Lurk, we can commit to a function. So here's a function that squares its argument and adds 7 to it, and we get a commitment to that. And to show you how that works, just as before, I can open the commitment and then immediately apply it to 9 in one case or 11 in another case. I get a different result. So I've told you I'm going to use this function, and then later I can open it for you on a single input, and you'll believe that this is the same function every time, but you'll only get a little bit of information about that function. And furthermore, we can do something really funky, which is what I call higher order functional commitments, which is that we can make a commitment to a function that takes a function as an input and does something with it. So this seems really obvious if you know Lisp and you know that Lurk is a Lisp and you followed all this, but this is a very weird thing to be able to do so simply. And I'm claiming that it's interesting and cool. So in this example, I bind some secret data to a value 555, and then I create an interface to that in the form of a function that takes a function and applies the function to the secret data. So then when I open that function and pass it a function that adds 111 to its argument, I get back a result. So I don't know. I think that's cool. Here's an example of functional commitments generally that comes from a paper called Efficient Functional Commitments. You should read it. It's really interesting. It goes into an approach to functional commitments that kind of inspired us to use these examples. So the credit bureau example is essentially, imagine that I'm a credit bureau and I have a secret proprietary scoring algorithm, and I want to give people credit scores, but I need to prove that I'm fairly applying the same credit score to everybody's data. So I can do this with the functional commitment. I commit to the function, and then the data is passed in. I get the result. You don't learn what the function was, but you are convinced that the output was correct. So just to make a complex enough example, I implemented reduce map, and then made from that map reduce, and then create my secret function is going to be one that takes the sum of the squares of the data. And you can see if I make this functional commitment opening, there it is. I get the result, but nowhere in this first line, which is essentially the input that the verifier sees, do we see what the function was. So we've accomplished the goal. That's one aspect of privacy. In the credit bureau example, you can imagine that the credit bureau wants to protect its privacy. But in the real world, there's also the opposite situation where maybe people want to protect the privacy of their data and the function is public. There are other ways of doing this in an ad hoc way, but I just wanted to show that because we have higher order functional commitments, we can actually do this in a really simple way as well. So in this case, we create a function that has an interface to the credit data, just like what I showed before, and then we're going to pass in publicly. Oops, I'm going the wrong direction. Now we're going to pass in this credit score function that's public, and we're going to get a result of applying that credit score function to the secret data. And again, we could arrange an ad hoc program that did that in a different way, but this is just a good example of the kinds of extra things you can do if you have these higher order functional commitments. And now I'm just going to talk a little bit about our collaborations and other use cases for Lurk. And you're going to hear from all these people later, so this will just be a teaser. Well, most of these people. So one thing that's really interesting about this project and the teams that have gathered around working on it is that we have a stack and an ecosystem that really spans abstraction layers from very abstract to very concrete. And because we're working closely together and every layer is really focused on simplicity and trying to just do the job of its layer in a way that cooperates with the others, I think there's a really nice synergy that emerges, and I think that's what lets us get from very low level to very high level so quickly, as we'll review this afternoon. So we have Yatima, who's going to be going right after me, and they're doing general formal theorem proving that you can get zero-knowledge proofs of. Then we have Glow, who's making efficient decentralized applications using Lurk. There's the programming language itself, which is the Lurk evaluator I've showed you. And then there's a zero-knowledge application, which is the circuit that lets you get proofs of that. And that's all riding on top of the fundamental zero-knowledge cryptography provided by Nova. You'll hear from Srinath Sethi of MSR. We actually theoretically can support many backends, but we're really focused on Nova right now. So that's the stack that you're going to see here. And then we're going to hear about optimized software in the form of GPU provers and optimized physical hardware in the form of ASIC provers from Supranational. So we're going all the way from custom silicon to math in a few short hops, which is exciting to me. One of our collaborators is not talking today, but she's doing a lot of the work behind the scenes, is Nada Amin. She's a programming languages specialist. She's working on the core language development, a Lisp-based version that allows for a lot of rapid prototyping, working on optimizations of Lurk in Lurk, and on this RAM subset that's going to give us a more ergonomic machine and easier ways of creating libraries, things like that, and including macros, everybody's favorite Lisp tool, which you'll be able to use just the way you think you should if you're into Lisp. Yatima, I'll say very little about them. I'll just flash these slides because they're going to tell you about themselves. But you can see they're doing some cool stuff with WASM and EVM, compiling down to Lurk, and we believe it's going to be kind of trustworthy because they're formally verifying it. Mutual Knowledge Systems are the makers of Glow, and they're doing this smart contract work that Marcin's going to show you. And then Srinath is going to talk about Nova, which is a really, really cool proving system, I think. It's very simple. You can actually read the paper and understand it. When we first saw the Nova repository, he made it public for us, and we're looking at it and we kind of said, okay, but where's the code? It's that simple. And it's gotten a little bigger since then, but it remains simple at heart, which is cool. That's kind of in keeping with the principle of our stack. And then Supranational, as I mentioned before, they're also working on VDF, a computational VDF, and that's where a lot of the technical ideas for this work came from, because we need the IVC-based recursive SNARKs for the VDF proofs as well. These are just some of our use cases. Filecoin's working on something called hierarchical consensus, and in order to make the proofs of that quickly verifiable and reliable, they think they need something like Lurk, so we're collaborating with them on that. Filecoin Green is basically a project to help people gain confidence that the data they're storing has certain carbon emission properties, and they have a project that wants to use Lurk to help with making those proofs reliable, while also allowing people to expose some of their calculations without necessarily showing all the logic of where they come from. And then this is a cool thing that came out of the event where I gave the first talk, which is this Foresight Intelligent Cooperation. We were brainstorming about zero-knowledge machine learning, and so we have some people who are kind of working up applications of that Lurk will be well suited to because of its flexibility, and you can read those here. All right, and future directions. So these are just, don't take these too seriously, but these are our goals for the next few quarters. We're looking to release a 1.0 version of Lurk that should be usable in production. It may not perform the best, but will have been audited, and you'll be able to write non-trivial programs of the kind that I've been showing by the end of the year. As features become available in Nova, we're going to be able to perform a lot of optimizations. So when you need to do something that's very compute intensive, you can use specific optimized circuits to implement particular functions. So right now, using Lurk, there's kind of a trade-off for the generality and power. You sort of have to pay that even when you're doing things that don't require it. And this optimization will let us get away from that. As Nova adds more interesting, something closer to PCD, maybe not general PCD, but we call binary tree IVC, that'll let us parallelize the proofs, which is going to help a lot with performance. And we'd also like to integrate VDF support. Basically, we're just going to keep moving on the core language, and eventually, by the end of next year, hopefully release Lurk 2.0 and have it audited. And that should really be something you can do interesting things with. What we'll have for next year and going on to the FVM is going to be great. I recommend you play with it. But the important thing to know is that the language is going to keep improving. It's going to get more expressive. We're going to take on more interesting domains, and the performance and costs are going to go down. So if you take one thing out of it, if you can program it, you can make a proof for it. And maybe today the applications that's practical for are going to be limited, but over the next couple years, you're going to be able to do extremely interesting things. So it's a good idea to start thinking about your problems, playing with it, and maybe going after some of the low-hanging fruit that doesn't require intense computation. Like, for example, Glow doesn't require extremely good performance out of the proofs, so they can do really interesting things with it. And that's it. I actually got through that with time to spare. So if anybody has questions, Sam will ask you for the questions.
So I'm wondering, what is the size of the proof? And does it depend, for instance, on the number of iterations?
The proof itself?
Yeah.
Okay, so I believe the current proofs are going to be something like 10K right now, but there's a lot of modifications on that. So it doesn't depend on the number of iterations. It does depend on how many iterations we've chosen to put into one concrete circuit. So remember that we have this kind of what I call an inner circuit that does one reduction step. For efficiency purposes, we might want to do 10 or 100 or 1,000 of those in one actual circuit. That will amortize the recursive overhead. So it's going to be something on the order of 10K with the current so-called final SNARK, which is just a detail of how Nova works. Srinath might talk about it, but he has another version in the works that for a little more prover time can get the proof down even smaller, maybe down to like 3K or something like that. So it depends a little bit on the size of the circuit and a little bit on choice of the final SNARK.
Right. And what kind of trusted setup does this require?
No trusted setup. Okay, if you want to use GROS16, and you could, we actually have a GROS16 implementation. It won't be true IVC because you need memory. You need to store all the intermediate proofs, but you can aggregate them with SNARKPack, which is a proof aggregation technique that we use in Filecoin. It was developed at Protocol Labs, kind of, from papers that other people wrote. You can use GROS16. If you were going to do that, you would need to make you would need a trusted setup for that inner circuit.
Thanks.
So from what I understood, the simple SNARKs only worked for like simple programs on finite data, right? But like for general like recursive SNARKs, it can work on programs on like arbitrary data structures, right? Lists and trees and stuff like that. So I just wonder, because you said something about cons being just a hash of the two expressions. So I wonder like how do you get like how you can do like car encoder, like the accessors? Like how does it work? Is it like through you look at the environment through hashing? I didn't really understand this.
Okay, so
sorry. The last thing was like if the primitive data types are only finite fields, or it could be like general like integers, or yeah. So that was the question.
Okay, so first part, I can try to walk you through the cons example in a little more detail. So let's pretend for the moment that our only data type is numbers, and we don't have type tags, and we know that this thing is going to be a cons. So imagine we take a binary hash. So let's say our numbers are 1 and 2. So we slam those together and make a binary hash of 1 and 2 concatenated with each other, and then we get some number, right? So this now is effectively the pointer to the cons. So let's say that the program I want to prove is it could be either car this pointer or cdr this pointer, and then we want to get respectively either 1 or 2 as a result from that. So in either case, the proof has to do essentially the same thing. Okay, at the point that it's figured out what instruction it's doing, we'll be on some reduction frame, and we'll have that we'll have the digest, the pointer there, and then there will be some code that proves the preimage. So the prover has to know that 1 and 2 are there. The prover actually has access to that memory somewhere. I mean, you could just brute force it, but it'll take a really long time, and you can prove anything. So in reality, with good cryptographic functions, the only way you'll be able to prove this destructuring or this lookup is if you already know, you have it written down somewhere in your desk drawer that 1, 2 hashed gives me this. So now I make a proof, and I just assign them into variables in the circuit. I just say, car is 1, cdr is 2, and then I say, oh, what was I doing? I look at my continuation, and it says, oh, I wanted the cdr. Okay, I'll give you 2. Okay. Does that make sense?
Kind of, yeah. I think I understand more or less, yeah. So.
I've managed to forget your second question.
Oh, it was just about if the primitive data types, it's just general like integers or only finite fields.
Yeah, so you can implement general integers with only finite fields. In fact, as you well know, we don't even need finite fields at all, right? Because we could do it all with lambdas if we wanted to do fancy stuff with church numerals and things like that. Yeah. But we don't have to do that. I was just pointing out that we can do it. We know we can do it even without the finite fields. But as a more optimized thing, for example, you could imagine that we're going to define like a infinitely large big num type that is a list of finite fields, or probably of fixed width integers, which we're going to be supporting hopefully for 1.0, because it'd be very useful to have 64-bit or maybe 128-bit integers, and then from that we can implement big nums of a fixed size or of no fixed size, and then you just write as a library, a numeric tower that could deal with those.
Okay, cool. Thank you.
You're welcome.
Thank you for the talk. It was great. If I'm not mistaken, so like in work, so memory is Merkle-based hashed, yes? And my question is, what is the current limitation of work in terms of memory? How much memory is could used, and maybe you could also answer a question, what other limitation of work, what can I do with work and what I can't?
So as far as memory, I honestly couldn't tell you what the limitation is. And the main reason for that, I think, is that we mostly run relatively small problems, small programs. And so essentially we have what we call a store, which basically allocates all the memory that it needs, keeps it around, makes the proofs, and then throws it away. So the important point is, at the scale that you're probably doing it, the memory is not likely to be an issue. And if you're doing really long proofs, you'll be breaking them up and parallelizing them in some way. But more or less, there's a little bit of overhead for this thing, but we're somewhat efficient because we don't... just think that there's a data structure that holds all of these things and has some indexes around it. So it's a little bit more than just the raw data needs to be, but there's not a terrible amount of overhead. And then your second question was, what is it good for? Like, what kind of programs can you? So I really want to stress, I think the answer is almost whatever you can think of. We're going to be on the FVM. You'll be able to write smart contracts. If in the course of writing a smart contract you think, wouldn't it be cool if I could insert a zero-knowledge proof here or have some private data, this will give you that power. I think people in Web3 probably think about this more than I do. I just said, like, here, do whatever you want. But some really good examples will be, I think, Yatima is going to show that not only can you do whatever you want, but you can have really high confidence that it is what you wanted. And Glow is going to show some examples of exactly how that kind of thinking can be useful in a blockchain context.
Thank you.
You're welcome.
Anyone else? If not, then we can move on to the next speaker.